Today we are going to discuss introduction to AVL tree. So AVL tree is a special kind of binary search tree. So it is named after Adelson, Welsky and Landis. These two scientists have developed this AVL tree, and based on their name, the nomenclature has been AVL tree. So this tree is basically in this tree, AVL tree, the height of two child subtree of any node differ by at most one. So if any at time they differ by more than one, then rebalancing will happen. Okay, then rebalancing will happen. So rebalancing is done to restore the property of the AVL tree. So AVL tree basically we can perform lookup operations, which is basically a search operation, insertion operation and deletion operation also we can perform on AVL tree, and all operations takes actually log n time, which is quite similar with BST. Okay, BST also, if you want to delete or if you want to update any nodes, it is big of log n time. AVL tree is named after its two Soviet inventors, Georgy Adelson-Welsky and Landis, who published this work in the research paper in 1962. The title of the paper is an algorithm for organization of information. Okay, so AVL tree is sometimes compared with red-black tree. So in some syllabus you will find red-black tree, and some syllabus you will find AVL tree. Both this tree, the working principles is almost like same. Some similarity is there, okay, because both support the same set of operations and take ON for basic operations like delete, insert, all these operations. Now in this AVL tree, one particular factor is there, which is called balance factor. So what is balance factor? In a usual binary tree is that in a binary tree, the balance factor of a node X is defined to be the height differences. So in particular node X, let's say here it is node X, and it has let's say one left subtree and one right subtree. So whatever the height of this difference, height difference of this left subtree and height difference of this right subtree, this will be called the balance factor. So in AVL tree, this balance factor is important. So balance factor is equal to height of the right subtree X and minus height of the left subtree X of its two child subtree rooted at node X. Just now I showed you how the difference of the height that is the balance factor. So any node X with balance factor less than 0 is called left heavy. One with balance factor greater than 0 is called right. So any node X with balance factor less than 0 is called left heavy, and one with balance factor greater than 0 is called right heavy subtree. And if balance factor is equal to 0 is sometimes simply called balanced. Okay, so balanced tree is always better, that we have seen in quicksort algorithm. If the tree is balanced, then time complexity is always less. So condition for AVL tree, there is two conditions. One is two conditions for the AVL tree. First is that it has to be a binary search tree. First condition, without binary search the AVL tree is not possible. Second one is height of the left subtree and height of the right subtree. The difference should be -1. That means height of the left subtree and height of the right subtree, the difference would be -1, 0 and 1. If it is anything less than or greater than this, then that is not a AVL tree. So in this case, condition 1, you can see that let's say we are going to insert A, B, C in a binary search tree, and it is in alphabetical order. That means let's say the weight of B is more than A and weight of C is more than B. So in that case, we will form the binary search tree like this: A, B, C. Okay. Now you can see that when we insert first time A, node A, the balance factor is 0 because A's left subtree is not there and right subtree is also not there initially. So it is the difference is 0. So balance factor is 0, left subtree and right subtree. When you insert B, then B's balance factor is 0 because it doesn't have any left subtree or right subtree. Whereas for A, there is no left subtree but right subtree is 1. A to B lies the height of the, the height of the right subtree is 1. So in this case, when A is normally inserted single node, then height of the left subtree and height of the right subtree both are 0 and 0, and the balance factor is 0 minus 0, 0. When it is a single node A. When you insert B, that times although B is having the balance factor 0 because it doesn't have any left subtree or right subtree. Okay, but for A, there is no left subtree but there is one right subtree, height is 1. That means 0 minus 1, this is 1. Okay, 0 minus 1 equal to minus 1. So minus 1 is fine because minus 1 is included. That means still the node A is balanced, and node B is obviously balanced because it has balance factor 0. Whereas node A's balance factor is minus 1, but still it is balanced. Okay. Now next, if you insert C, then you will find that the balance factor will be violated. So how? So you can, in case of C, balance factor is 0 because it doesn't have left subtree or right subtree. In case of B, balance factor is minus 1 because it doesn't have any left subtree but it has right subtree 1. That means 0 minus 1. 0 minus 1 is 1 for this one, B. But what is the balance factor of A? A doesn't have any left subtree. That means 0. But it has 1, 2. Height, right subtree height is 2 on node A. Okay, height of the right subtree is 2. This 1 and this 2 for A. That means 0, left subtree is 0, which is true only. Right subtree is minus 2, so 0 minus 2 minus 2. Once it is minus 2, it goes beyond this range, which is minus 1, 0 and 1 because it is minus 2. So once it is minus 2, then the balance factor will be compromised. That means it is no longer a balanced tree. Okay, it is no longer a balanced tree. This node will be violated. So this is imbalanced node. So we have to do something about it. You have to make it balance. So you understood this now. So initially it is 0, 0. When you insert B, it's minus 1. When you insert C, then only A becomes unbalanced because it is the balance factor of A becomes 0 is the left subtree and right subtree is 1, 2. So it is imbalanced now. So minus 2. So what you have to do? So in this case, so make the above tree balance, there will be a left rotation rooted on B. That means the middle element you have to take and you have to pull up, and this A has to go left side. So this left rotation will happen. So B will be going up. So B will be going up. Here you can see. So B will be going up, and because it has a left rotation, so A will come here because also you have to remember that it has to be a BST. Sorry. Also you have to remember that it has to be a BST. Once you do the rotation, it has to be a BST. Okay. So this is a BST because A is less than B and C is greater than B. So we have a maintain BST properly. So in this case we will call left rotation. Okay, this is left rotation. This is left rotation. So it is left rotation. Okay. Now let's say scenario is something like this. C is the top node, and we inserted like this. C has come first, and we have to insert CBA. So CBA, in this case you can see the balance factor of A is 0 because it doesn't have left or right subtree. In this case balance factor is 1 because this is 1 and this is 0. So 1 minus 0, it is 1 only. What about balance factor of C? Balance factor of C is again compromised. That means it is neither minus 1 nor 0 nor 1. Rather this is 1, 2 minus, this side nothing is there. That means 0. 2 minus 0. That means it is basically 2. So balance factor is 2. Once balance factor is 2, it is not in this particular set, minus 1, 0 and 1. So it will become a imbalanced tree. So in that case you will be having a right rotations. In this case, we'll be having a right rotation. That means B will be the middle node, C will come right, and A will be left side of B. So you have to do a right rotations. This is a right rotations. Okay, so this is B A C. So we'll call above rotation as right rotation. So we just saw left rotations, and then we saw right rotations, and finally we have another rotation which is called now third condition. Third condition is, let's say you have inserted A, and then you are going to insert A, B, C, and A is there, and then C is greater than A, and B is less than C. So this is already right left rotation is there. So this type of tree need two rotations. So first one would look like this, A, B, C. Okay, A, B, C, and once this A, B, C comes, then you have to do the left rotation, which you already saw in the first case. So in this case, you see here, first you have to do a right rotations. Okay, so once you do the right rotation, then what will happen? Once you do the right rotation here, okay, right rotations. So in this case, this B will be come here, and this will be C will be here only. Okay, so this figure is basically as same as the first condition that is. So it is in, so in this case, first of all you have to understand what is the height. So A's height is -2, because left side there is no sub, so 0, right side is 1 1 2, so 0 -2 -2. That means this node, A node, is imbalanced or unbalanced. So this node you have to, so for this we have to do what? We have to do rotations. What rotations we will do? Because it's a binary search tree, so we will take this B and we'll push it up, and then we'll take C down, because anyway C is greater than B, C is greater than B, and B is greater than A. That is the binary search tree property, and we have inserted data like that. So it has, B has come here, C has come down, and A is already, so still it is -2, because balance factor of A is -2, because left side no subtree 0 -1 2, 0 -2 -2. This is 0 -1 -1. This is fine. Node B is fine. Only node A has a problem. So now it is as similar as the earlier, the first case. So what we'll do? We'll do the left rotation. So first we did the right rotations here. First we did the right rotations, and B comes in the middle and C comes the last, and then we are having left rotation. So it will be calling right left rotation. So once this is done, then you can have right rotation. You see here, once this is done, this is very known figure to us, because our first condition is this only. So what you have to do, once you bring this figure here, now it is as similar as the first condition. So you have to just do a left rotation here. Okay, left rotation on node B. So if you do that, it look like this. So B, all balance factors are 0 0. So this is right left rotations. And finally, condition 4 we have this one, we have fourth condition, which is we are inserting C, and then A, and then B. In this case, what we'll do, we'll first, so this is what we'll do this, you can see that fourth condition, which is we have A, C, and then we have A, and then we have B. Okay, so we have B. So here what you have to do, we have to first, so this is left and then right. So left right is there. So what we'll do, we'll do a right, we'll do a left rotation first, like this. We'll do a left rotations. By this left rotation, what we'll do, we'll bring this B here, instead of A will be having B here, and then A will be coming left side of B. Okay, this is A will come, and B will be here. So it will look like this, C, B, A. Obviously the height here, actually the balance factor is 2, because initially it is 1 2. That's why node C is unbalanced. So you have to do the rotations. What rotation we will do? First we will do the left rotations, where this B will come up, and then A will come down, left child of B. So this will look like this. Now it is exactly the second condition. What you have to do? You have to just do a right rotations. By pulling right rotations, you have to bring B up, and A left side and C left side, which follows the BST property, and the balance factor is 0, left subtree minus right subtree, left subtree right subtree 0, left subtree right subtree 0. That means subtraction of left subtree and right subtree is 0. That means this balance factor is 0, balance factor is 0, balance factor is 0. So there are 4 conditions that I showed you for inserting element in a AVL tree. Okay, so thank you very much.